Yo! Welcome to AP Calculus Lecture 1.4a. So that the way the numbers work is we're in section 4 of chapter 1, and this is the first lecture from that section. We're going to be working problems from page 76, so get your book out and turn it to 76. And this lecture is called One-Sided Limits. Okay. So it is useful to examine limits from strictly the left or the right side. Such limits are one-sided limits. Okay, we're going to draw a graph here. And I'm going to draw a function that looks something like this. So we're going to have a break in it, a couple of holes, let's put another hole there, and then it keeps going forever. We'll call that f of x. Okay, right here on the x-axis, we'll call that point A. Point B, and lining up with this second hole is point C. And then I'm going to call right here L, R, S, and lining up with this hole, we'll call that T. Okay, so let's take a few limits here. So the limit as x approaches b of f of x, what is that? You look at the graph and you tell me first. All right, so we're just saying, what is the y value as x approaches b? Well, let's look up at the graph. And you can see that it would be, I didn't do a great job of drawing it, but it would be S. That's the y value as x approaches b. Now, how about the limit as x approaches c of f of x? Okay, well, it's okay that there is, as x approaches c, you go up here, it's okay that there's a hole there because there's no jump or break. Your hands come together at, and what I mean for this to be, and I'm a little off there, but what I mean, it is T. So at B it was S, the y value is T. So let's do a little note here. The function is undefined at t, but the limit exists because your hands come together on the graph there. All right, how about the limit as x approaches a of f of x? Well, from the left side, you have L, and the right side, you have R. Your hands don't come together, so it's does not exist. Hands don't come together at A. Okay, and let's write this down a little more. Let's say, so we don't get any good information when we just take the limit as x approaches A. But although the limit does not exist at A, the left-handed limit might. So doing this as x approaches A doesn't really tell us much about the function, but how about we do this? Let's take the limit as x approaches A, and then I'm going to put a minus sign there. That minus sign means from the left. Okay, I bet you can figure out what the plus sign would mean. So of f of x. So if we're coming only from the left side here, the limit is L. How about we take the limit as x approaches A, and we'll put a plus sign. The plus sign means from the right. So of f of x. Well, what's that going to be if you're coming from the right? Well, the y value, if you're only coming from the right, at A is r. So yes, the limit doesn't exist at A, but if you take it from the left and from the right, you can get more information about the function. Okay? So this would be called the left-handed limit, and this is the right-handed limit. So that's why we used L and R. Okay, so run out of space, so we'll erase and move on. So just a couple of more sentences, and we'll start doing example problems from the book. So the left-handed limit is the value and of course this would be the y value you approach, because remember the limit is just the y value, when coming only from the left. The right-handed limit, I'll bet you can write this sentence yourself. Is the y value you approach when coming only from where? So from the right. So a left-handed limit and a right-handed limit, you might be able to get an answer there. But that doesn't mean that the limit exists. A limit exists only if the left-handed and right-handed limits are equal. So you analyze it from the left, from the right. If they're equal, then the limit exists. All right, let's do some examples from the book. So our first example is number 6. On page 76. So we've got that is a graph. And the instructions are for part A, the limit as x approaches c from the right, part B from the left, and then part C, just the limit as x approaches c. Okay, so from the right, we're coming from the right. C is, in this case, -2. So when x is at -2, what's the y value when you come from the right? It's also -2. Let's come from the left, part B. We're coming from the left. When we get to -2 on the x value, the y value also -2. So the right-handed limit is -2. The left-handed limit is -2. How about when you come from both sides? Well, when your hands both get there, I'll use markers instead, the limit is also -2. There's no break in the function. So in this particular case, since there's no break in the function, the answer is the same on all accounts. -2, -2, and -2. That's the y value is true for all three. Now let's look at one where that's not the case. Peer down at number 10. If we come from the right, so c is -1, so we're concerned with when x is equal to -1. When we come from the right, the y value when we get to -1 is 0. Okay, we're at 0 here on the y-axis. When we come from the left, part B, the y value when we get to -1 is 2. So there's a big jump in the function. So the answer to A, 0. The answer to B is 2. The answer to part C, well, our hands don't come together, do they? Stops right there, stops right there. They're two different values. One is 2, one is 0. So there's a gap in the function. So part C is does not exist. All right, so part A is 0, B is 2, and then C does not exist because the left-handed and the right-handed limits are not equal. So let's do a summary of evaluating limits. What are the possibilities? You can get, when you plug in the form 0 over 0. That is indeterminate. We've done a lot of those, right? And that means it needs more work. So we're going to have to maybe put some algebra on it to figure it out. You can also get a situation where you have not 0 over 0. Well, that is the limit does not exist. If you get not 0, 5 over 0, whatever, the limit doesn't exist. The limit's undefined. And then you can also get a form 0 over not 0. In that particular case, the limit is just equal to 0. Because 0 over a number that's not 0 is 0. Okay, so that one's easy. That one's easy. This one requires more work. Okay, let's move on to some more examples. Right, number 12. On page 76. Okay, the instructions say, so we've got the limit as x approaches 2 from the right of 2 minus x over x squared minus 4. So you plug in a 2 here, you're going to get 0 over 0. So this one needs more work. Now let me tell you, let's write this down. If the function does not have an absolute value in it, or is piecewise, you work the problems the same way. So the same way as what we did in section 1.3. Okay? So all we have to do here, we take the limit as x approaches 2 from the right. 2 minus x, we could factor that into x plus 2 times x minus 2. And then hopefully you can see that you could factor out a negative 1 and make it x minus 2. That'd be negative x plus 2, which is the same as that, over x plus 2, x minus 2. The x minus 2 is a cancel as long as x does not equal 2. And then you could take the limit as x approaches 2 from the right of negative 1 over x plus 2, and that's going to be negative 1/4 when we can now plug the 2 in. So no difference. If you did 2 from the left, you'd get the same exact thing. Okay, there's no difference. It's only when there's an absolute value symbol in the problem or it's a piecewise function that we have to do things any different. All right, let's go ahead and do one more that's just like what we've been doing. Let's try example 14. So that is the limit as x approaches 4. And I'm going to tell you, in my book, I really can't tell if there's a positive or a negative sign there. It looks like maybe there's a negative sign. It's really light in my book. So root x minus 2 over x minus 4. But since there's no absolute value, it's not a piecewise, it doesn't really matter. We can just treat it like it's a 4. Well, this one, if you plug a 4 in, you're going to get 0, 0. So this is one, there's a radical involved. You might want to think, maybe conjugate. Let's try multiplying it by root x plus 4 and see if we can get rid of that radical. Okay, root x times root x is x. And then the, let's see, that would be, I'm so sorry. Apologize for that. It'd be 2. As I FOILed it out, I saw, hey, the middle term doesn't go away. And I knew I did it wrong. So negative 2 times root x and then positive 2 times root x, the middle term goes away. And then minus 4 when you do the last there. And then I'm not going to multiply out the bottom because I want that x minus 4 to cancel. All right, so x minus 4 cancels as long as x does not equal 4. And I have the limit as x approaches 4 from the left of 1 over root x plus 2. Now we can plug in square root of 4 is 2, so that would be, in this case, positive 1/4. All right, boom. So that just gave you a little practice from last section. Now let's do a couple where we do have to analyze it from the left or the right. So this is really the new stuff. Okay, let's look at example 16. We're still on page 76. So 16, we've got the limit as x approaches 2 of the absolute value of x minus 2 over x minus 2. Okay, so what you have to do in this case, there's an absolute value. We need to take the limit from the right and from the left. So 2 plus, right? Well, what you want to think about is that this is a number that's just a little bit over 2. Let's think 2.001. Okay, that's a little bit over 2, right? Coming from the right, or correct. Okay, so if you plug in 2.001 in here, something a little bigger than 2, what you're going to get on top is a tiny positive number. And then what you're going to get on bottom is a tiny positive number. Well, a tiny positive divided by a tiny positive is just 1. So from the right, it's 1. Now let's look at it from the left. So as x approaches 2 from the left of the absolute value of x minus 2 over x minus 2. Well, from the left, that's just a little less than 2. Let's say 1.999. Well, if I plug in 1.999 minus 2, I'm going to get negative 0.001, right? But the absolute value makes it a positive, so it's still a tiny positive. But on the bottom, there's no absolute value symbol. So I would have a tiny negative number. A tiny positive divided by a tiny negative is going to be negative 1. So these are not equal. So the limit does not exist. All right, you need to show that work, but the answer is does not exist. Okay, so this function has a gap in it at 2. Your hands would not come together. All right, let's take a look at a piecewise function. So that's going to be example 20. So for that one, we have the limit as x approaches 2. And it is x squared minus 4x plus 6 when x is less than 2, meaning from the left, and then negative x squared plus 4x minus 2 when x is greater than or equal to 2. So that would be from the right. Because x is greater than 2. Okay, so we have to do them separately. So as x approaches 2 from the left, we would have x squared minus 4x plus 6. And there's no denominator. We can just plug 2 in. So that's going to be 2 squared minus 4 times 2 plus 6. That's going to be 4 minus 8 plus 6, right? So that is 2. And then we'll take the limit as x approaches 2 from the right. And our equation is negative x squared plus 4x minus 2. So that'd be negative 2 squared plus 4 times 2 minus 2. That's going to be negative 4 plus 8. That's 4 minus 2, which is 2. So they are equal. So since they're equal, your hands come together there. So the limit is equal to 2. If they were different, then it would be does not exist. But since they're the same, the limit's equal to 2. All right, that's it for this lecture. The homework is page 76. And I'm going to have you do 5 through 24, but you're going to remove all these examples I just did. So except 6, 10, 12, 14, 16, and 20. So all the examples I did in your notes, don't do those again. But everything else, do both the odds and the evens, do 5 through 24. All right, that does it and for this lecture, and I'll be making the solutions video for this homework shortly.